Triatomic hydrogen, or H3, is an unstable triatomic molecule containing only hydrogen. Since this molecule contains only 3 atoms of hydrogen, it is the simplest triatomic molecule, and it is relatively simple to numerically solve the quantum mechanics description of the particles. Being unstable, the molecule breaks up in under a millionth of a second. Its fleeting lifetime makes it rare, but it is quite commonly formed and destroyed in the universe thanks to the commonness of the trihydrogen cation. The infrared spectrum of H3 due to vibration and rotation is very similar to that of the ion H3+. In the early universe, this ability to emit infrared light allowed the primordial hydrogen and helium gas to cool down so as to form stars. Formation. The neutral molecule can be formed in a low-pressure gas discharge tube. A neutral beam of H3 can be formed from a beam of H3+ ions passing through gaseous potassium, which donates an electron to the ion, forming K+. Other gaseous alkali metals, such as cesium, can also be used to donate electrons. H3+ ions can be made in a duoplasmatron, where an electric discharge passed through low-pressure molecular hydrogen. This causes some H2 to become H2+. Then H2 plus H2 plus H3 plus H. The reaction is exothermic with an energy of 1.7 electron volts, so the ions produced are hot with much vibrational energy. These can cool down via collisions with cooler gas if the pressure is high enough. This is significant because strongly vibrating ions produce strongly vibrating neutral molecules when neutralized according to the Franck-Condon principle. Properties. The molecule can only exist in an excited state. The different excited electronic states are represented by symbols for the outer electron Ni gamma, with N the principal quantum number, L is the electronic angular momentum, and gamma is the electronic symmetry selected from the D3H group. Extra bracketed symbols can be attached showing vibration in the core. SDL, with S representing symmetrical stretch, D degenerate mode, and L vibrational angular momentum. Yet another term can be inserted to indicate molecular rotation, with N angular momentum apart from electrons as projected on the molecular axis, and G the Huygens convenient quantum number determined by G equals L plus lambda K. This is often, as the rotational states are restricted by the constituent particles all being fermions. Examples of these states are 2 SAR1, 3 SAR1, 2 picoamperes, 2, 3 de, 3 de, 3 deciamperes, 1, 3 p, 3 picoamperes, 2. The 2p2a2 state has a lifetime of 700 nanoseconds. If the molecule attempts to lose energy and go to the repulsive ground state, it spontaneously breaks up. The lowest energy metastable state, 2SAR1, has an energy minus 3.777 electron volts below the H3+ and E- state but decays in around 1 ps. The unstable ground state, designated 2p2e, spontaneously breaks up into a H2 molecule and an H atom. Rotationless states have a longer lifetime than rotating molecules. The electronic state for a trihydrogen cation with an electron delocalized around it is a Rydberg state. The outer electron can be boosted to high Rydberg state, and can ionize if the energy gets to 29,562.6 centimeters minus 1 above the 2 picoamperes 2 state, in which case H3+ forms. Shape. The shape of the molecule is predicted to be an equilateral triangle. Vibrations can occur in the molecule in 2 ways. Firstly, the molecule can expand and contract retaining the equilateral triangle shape, or one atom can move relative to the others distorting the triangle. The bending vibration has a dipole moment and thus couples to infrared radiation spectrum. Gerhard Hertzberg was the first to find spectroscopic lines of neutral H3 when he was 75 years old in 1979. Later he announced that this observation was one of his favorite discoveries. The lines came about from a cathode discharge tube. The reason that earlier observers could not see any H3 spectral lines was due to them being swamped by the spectrum of the much more abundant H2. The important advance was to separate out H3 so it could be observed alone. Separation uses mass spectroscopy separation of the positive ions, so that H3 with mass 3 can be separated from H2 with mass 2. However, there is still some contamination from HD, which also has mass 3. The spectrum of H3 is mainly due to transitions to the longer-lived state of 2p2a2. The spectrum can be measured via a two-step photoionization method. Transitions dropping to the lower 2s2a1 state are affected by its very short lifetime in what is called pride association. The spectral lines involved are broadened. In the spectrum there are bands due to rotation with P, Q and R branches. The R branch is very weak in H3 isotope but strong with D3. The symmetric stretch vibration mode has a wave number of 3213.1 cm -1 from the 3s2a1 level and 3168 cm -1 for 3d2e. and 3254 cm -1 for 2p2a2. The bending vibrational frequencies are also quite similar to those for H3+. Levels cation. The related H3+ ion is the most prevalent molecular ion in interstellar space. It is believed to have played a crucial role in the cooling of early stars in the history of the universe through its ability readily to absorb and emit photons. One of the most important chemical reactions in interstellar space is H3++ E minus H3 and then H2 plus H. Calculations. Since the molecule is relatively simple, researchers have attempted to calculate the properties of the molecule ab initio from quantum theory. The Hartree-Fock equations have been used. Natural occurrence. Triatomic hydrogen will be formed during the neutralization of H3+. This ion will be neutralized in the presence of gases other than He or H2, as it can abstract an electron. Thus H3 is formed in the aurora in the ionosphere of Jupiter and Saturn. History. J. Thomson observed H3+ while experimenting with positive rays. He believed that it was an ionized form of H3 from about 1911. He believed that H3 was a stable molecule and wrote and lectured about it. He stated that the easiest way to make it was to target potassium hydroxide with cathode rays. In 1913, Johannes Stark proposed that 3 hydrogen nuclei and electrons could form a stable ring shape. In 1919, Niels Bohr proposed a structure with 3 nuclei in a straight line, with 3 electrons orbiting in a circle around the central nucleus. He believed that H3+ would be unstable, but that reacting H2- with H+ could yield neutral H3. Stanley Allen's structure was in the shape of a hexagon with alternating electrons and nuclei. In 1916, Arthur Dempster showed that H3 gas was unstable, but at the same time also confirmed that the cation existed. In 1917, Gerald Vent and William Duane discovered that hydrogen gas subjected to alpha particles shrank in volume and thought that diatomic hydrogen was converted to triatomic. After this, researchers thought that active hydrogen could be the triatomic form. Joseph Levine went so far as to postulate that low-pressure systems on the Earth happened due to triatomic hydrogen high in the atmosphere. In 1920, Vent and Landau named the substance hyzone, in analogy to ozone and its extra reactivity over normal hydrogen. Earlier, Gottfried Wilhelm Moissan believed he had discovered a form of hydrogen analogous to ozone which he called ozonocyst. It was made by electrolysis of dilute sulfuric acid. In those days no one knew that ozone was triatomic, so he did not announce triatomic hydrogen. This was later shown to be a mixture with sulfur dioxide, and not a new form of hydrogen. In the 1930s, active hydrogen was found to be hydrogen with hydrogen sulfide contamination, and scientists stopped believing in triatomic hydrogen. Quantum mechanical calculations showed that neutral H3 was unstable, but that ionized H3+ could exist. When the concept of isotopes came along, people such as Bohr then thought there may be an echahydrogen with atomic weight 3. This idea was later proven with the existence of tritium, but that was not the explanation of why molecular weight 3 was observed in mass spectrometers. J.J. Thomson later believed that the molecular weight 3 molecule he observed was hydrogen deuteride. In the Orion Nebula, lines were observed that were attributed to nebulae which could have been the new element echahydrogen, especially when its atomic weight was calculated as near 3. Later this was shown to be ionized nitrogen and oxygen. Gerhard Hertzberg was the first to actually observe the spectrum of neutral H3, and this triatomic molecule was the first to have a Rydberg spectrum measured where its own ground state was unstable.